A rod of length L and diameter D is subjected to a tensile load P. Which of the following is sufficient to calculate the resulting change in diameter? A. Young's modulus, B. Shear modulus, C. Poisson's ratio, and D. Both A and B. We know change in length del L equals to PL by AE. Here E is the Young's modulus. But in this case we have to find out the change in diameter. So using the longitudinal strain we have to calculate the lateral strain that is required. Also we know that Poisson's ratio mu equals to lateral strain by longitudinal strain. So we need both mu and E for this purpose. But this is not in the option. Also we know that E equals to 2G into 1 plus mu, where G is the shear modulus. So if we get the value of both E and G, we can easily calculate mu. So here option D, that is both A and B, is the right answer. A thin cylinder of inner radius 500 mm and thickness 10 mm is subjected to an internal pressure of 5 MPa. The average circumferential stress in MPa is option A 100, option B 250, option C 500, and option D 1000. We know the formula for circumferential stress is PD by 2T, where P is the pressure, that is 5 MPa, D is the diameter, that is 500 into 2 is equals to 1000 millimeter, as 500 mm is the radius and T is 10 mm, that is the thickness. So putting this value in the formula we get the circumferential stress is 250 MPa. So the answer is option B, 250. The total area under the stress strain curve of a mild steel specimen tested up to failure under tension is a measure of ductility, ultimate strength, stiffness, or toughness. Here the answer is toughness. You have to remember that toughness is the ability of a material to absorb energy before fracturing and absorb energy per unit volume, and it is calculated by area under the stress strain curve. So option D, toughness, is the right answer here. A steel bar of 40 mm cross 40 mm square cross section is subjected to an axial compressive load of 200 kilonewton. If the length of the bar is 2 meter and capital E equals to 200 GPa, the elongation of the bar will be option A 1.25 mm, option B 2.70 mm, option C 4.05 mm, and option D 5.40 mm. Here we know that del L equals to PL by AE, where del L is the change in length or the elongation of the bar here. Here P is equals to 200 kilonewton, that is equals to 200 into 10 to the power 3 Newton. L equals to 2 meter, that is 2000 millimeter. E equals to 200 GPa, that is 200 into 10 to the power 3 Newton per millimeter square. And A, that is area, equals to 40 cross 40. So after putting all the values in the above formula, we get del L equals to 1.25 mm. So option A, 1.25 mm, is the right answer. Young's modulus of a wire is defined as the stress which will increase the length of wire compared to its original length by option A half, option B same amount, option C double, and option D 1/4. So we know that Young's modulus equals to stress by strain. Now we can replace strain by del L by L, that is change in length by original length. In this case, for E equals to sigma, that is for Young's modulus equals to stress, the value of del L should be equals to L. So the increase in length must be equals to original length. So option B, that is same amount, is the right answer. The intensity of stress which causes unit strain is called unit stress, modulus of rigidity, bulk modulus, modulus of elasticity. We know E is equals to sigma by epsilon, that is stress by strain. So for unit strain, E equals to sigma. So here the answer will be modulus of elasticity. That means the intensity of stress which causes unit strain is called modulus of elasticity. Option D. When both ends of the column are fixed, the effective length is option A, its own length, option B, twice its length, option C, half its length, and option D, 1 by root 2 into its length. Here the condition is given both ends of the column are fixed. So in this case the answer will be half its length. The effective length is half of its length. But if the condition is both ends of the column are hinged, then the answer will be the effective length is its own length. And if the condition is one end of the column is fixed and other end free, then the answer will be twice its length. And if the condition is one end of the column is fixed and other end hinged, then the answer will be 1 by root 2 into its length. So here the answer is half its length. If the radius of wire stretched by a load is doubled, then its Young modulus will be option A doubled, option B halved, option C 4 times, and option D none of this. We know Young's modulus equals to stress by strain. If we replace the value of stress with load by area, that is P by A, we get E equals to P by A into epsilon. In this case, P and epsilon are constant and A equals to pi r square by 2. So if the radius is doubled, A will be 4 times. So as E equals to P by A into epsilon, so E will become 1/4. And it is not in the option. So option D, that is none of this, will be the answer. Poisson's ratio is the ratio of option A, stress and strain, option B, lateral strain and longitudinal strain, option C, shear stress and shear strain, option D, direct stress and volumetric strain. So Poisson's ratio is the ratio of lateral strain and longitudinal strain, and the ratio of stress and strain is called modulus of elasticity. The ratio of shear stress and shear strain is called modulus of rigidity, and the ratio of direct stress and volumetric strain is called bulk modulus. You have to remember all this. Longitudinal stress in a thin cylinder is option A, equal to hoop stress, option B, twice the hoop stress, option C, half of the hoop stress, and option D, 1/4 of the hoop stress. Here the answer is half of the hoop stress. If P is the internal pressure, T is the thickness of the cell wall, and D is the internal diameter, then hoop stress equals to PD by 2T, and longitudinal stress equals to PD by 4T. So that can be written as half into PD by 2T, that is half into hoop stress. So option C, half of the hoop stress, will be the right answer here. The bulk modulus of a material having E equals to 200 GPa and G equals to 80 GPa is option A, 160 GPa, option B, 233.3 GPa, option C, 133.3 GPa, and option D, 250 GPa. Here the answer is 133.3 GPa. We know E equals to 9 kg by 3k plus G, where K is the bulk modulus and G is the modulus of rigidity and E is the modulus of elasticity. So by putting the values in this equation, we can calculate the value of K, that is bulk modulus, equals to 133.33 GPa. The Poisson's ratio of a material having E equals to 200 GPa and G equals to 80 GPa is 0.15, 0.25, 0.35, 0.45. We know E equals to 2G into 1 plus mu, where E is the modulus of elasticity, G is the modulus of rigidity, and mu is the Poisson's ratio. So by putting the values in this equation, we can get the value of mu, that is 0.25. So option B, 0.25 will be the right answer here. The value of Poisson's ratio for cast iron is option A, 0.1 to 0.2, option B, 0.23 to 0.27, option C, 0.25 to 0.33, option D, 0.4 to 0.6. Here the answer will be 0.23 to 0.27 for cast iron, but the value 0.25 to 0.33 is applicable for steel. So the Poisson's ratio for steel is 0.25 to 0.33 and for cast iron is 0.23 to 0.27. Maximum normal stress theory is used for brittle material, ductile material, both, none of this. Maximum normal stress theory is applicable for brittle material. So option A, brittle material, is the right answer. But for ductile materials, we have maximum shear stress theory. The rate of change of bending moment is equal to option A, shear force at the section, option B, deflection at the section, option C, intensity of loading, option D, slope at the section. The rate of change of bending moment is equal to option A, shear force at the section. So here the answer is option A, shear force at the section. But if the question is somehow the rate of change of shear force is equal to, then the answer will be intensity of loading. Which one of the following has the unit Newton per meter square? Option A, stress, option B, pressure, option C, modulus of elasticity, and option D, all of the above. Here the answer is all of the above. We know stress equals to P by A, pressure is also equals to P by A, and modulus of elasticity is equals to stress by strain. But strain is unitless. So modulus of elasticity and stress have the same unit, and pressure has also the same unit. So option D, all of the above, will be the right answer here. Twisting couple in a shaft introduces in it option A, bending moment, option B, deflection, option C, shear strain, option D, shear stress. From the torsion equation, we know T by J equals to tau by R equals to C theta by L. So the twisting couple, that is a torque in a shaft, introduces tau, that is shear stress. So option D, shear stress, is the right answer here. 5 specimens of MS have their length and diameters as LD, 2L2D, 3L3D, 4L4D, 5L5D. Which of the following will have the largest extension for the same tensile load? Option A first, option B second, option C third, option D fourth, and option E fifth. We know del L equals to PL by AE. Here P and E are constant. Only L and A varies. Also A equals to pi d square by 4, where pi and 4 are the constant terms. So for del L1 it is equal to L by d square. For del L2 it is equals to L by 2d square. For del L3 it is equals to L by 3d square. For del L4 it is equals to L by 4d square. And for del L5 it is equals to L by 5d square. So the largest extension is in the first case. So option A, first, is the right answer. The value of modulus of elasticity for mild steel is in the order of option A 2.1 into 10 to the power 6 kg per centimeter square, option B 2.1 into 10 to the power 7 kg per centimeter square, option C 2.1 into 10 to the power 5 kg per centimeter square, and option D 3.8 into 10 to the power 6 kg per centimeter square. Here the answer is 2.1 into 10 to the power 6 kg per centimeter square. Shear force at any point on the beam is the algebraic sum of all the vertical forces, all the horizontal forces, forces on either side of the point, moment of forces on either side of the point. Here the answer is forces on either side of the point. So option C is the right answer. But if shear force is replaced by bending moment, that means bending moment at any point on the beam is the algebraic sum of, then option D, that is moment of the force on either side of the point, will be the right answer.